Hi. So let's get right into another example. So here we're going to compute the integral that is on the board, right? So the integral of y squared z ds over the curve C, where C goes from 312 to 125. Okay, so let's get right into it. So something I did not discuss yet is how to come up with a vector equation, a vector function that describes all points on your curve. If you're only given 2 points and you want to find the line that connects them. Okay, so this is, there's more than one way you can do it. Okay, you can either start at that point, right, 312, okay, and then you can take a direction vector, right? How do you get the direction vector? You take the difference between them, okay, and then you add until you get to the final point, okay, and you can do that, but from the book, the way the book does it is like so. Okay, I want you to realize that they're really the same thing, right? Because if I look at my t, okay, if I think of it like this, right? Group, okay, ignore the one part, 1 times 3. Sorry, video went out there for a second. Ignore the 1 times 312 part. Just ignore that for a second. Look at the T312 and the T125. Okay, so I'm really taking 125 minus 312, right? So that's final minus initial. That's a direction vector, right? That's a direction vector. And so you're starting at 312, right, with the 1 plus T in the direction vector, right? And so when t is equal to 0, you start here, and then when t is equal to 1, you get to your final destination. So another way of saying this is that I could also just as well have 312 plus t times the difference vector, which is 1 minus 3 is negative 2. 2 minus 1 is 1, and 5 minus 2 is 3. Okay, so I want you to take a moment just to realize that they're the same thing. They are identical, 2 different ways to think of it. So I actually prefer to think of it this way. Okay, so you start off with your starting point, and then it's plus t times the starting point plus t times direction vector, right? You start in one direction, you move with the direction vector, so your starting vector gets you here, then you move in a direction, and then when t equals 1, you're at your final destination. Now, the book wants you to do it this way. You're going to have 2 instances of t. 1 minus t and t. Now, once you do it this way, though, you're going to have to convert it to this anyway. Okay? You're going to have to convert it to that anyway. Why? Because you're going to have to compute derivatives. And you need to see x and y and z in very simple manners. Okay? So I recommend you just do it the second way. So you skip the first step, the way the book tells you. You just skip it. You do initial plus t times direction vector. Do it that way, but I'm including the first part because this is how your book does it, and I want you to be able to connect to different concepts, okay? So if you, I don't know, if you want a connection to the book, do it that way. Okay, so what is this? Well, what is R of t? R of t is x of t, y of t, z of t, okay? Put in a vector. So it has three parts, x, y, and z, and I put it in a vector. So the derivative of r, right, the derivative of r prime of t is the derivative with respect of x with respect to t, derivative of y with respect to t, derivative of z with respect to z, and this is just going to equal negative 2, 1, and 3. It's literally just the direction vector. Okay, so now that we have all this taken care of, we can actually get down to business. Okay, so what I want to do is I want to use this R of t as the parameterization of c. So I'm doing my integral from 0 to 1. Why? Because that's what I said a second ago. And if you look at this equation, it makes sense. If I plug in t equals 0, then this goes away, and 1 minus 0 is all 3, 1, 2. That's all it is. It's that vector. If I plug in t equals 1, it's going to kill off that vector, and it's going to be only this vector, 1, 2, 5. So there are two different ways to think about it. You start here, you end here, or you start here and you move in this direction until t equals 1. Okay? Hopefully I've beat that to death. You see that they're equivalent. I prefer this way. Okay. The reason I prefer it that way is because now I can look at this really easily and I can see, okay, x of t, this is 3 minus 2t, right? 3 minus 2t. Y of t, this is 1 plus t, 1 plus t. Z of t, this is 2 plus 3 of t. Okay, so now I'm going to go up here, I'm going to replace my y with 1 plus t, I'm going to square it, and then I'm going to plug in z, which is 2 plus 3t. So 2 plus 3t, and for the final part, I put the dx dt squared plus dy dt squared plus dz dt squared. Finally, dt. Okay, well, what is dx dt, dy dt, dz dt? Well, it's you take this, you take the derivative. What is it going to be? Well, the t is going to go away, and that's a constant, so that's going away. So really, x prime is negative 2, y prime is 1, z prime is 3. Okay, so that's what it is. I go over here and I just carry the calculation out. Okay, so this right here, this is a fairly routine calculation. Okay, but I'm not going to do it. It's just algebra. Okay, so it's going to turn out to be 3t cubed plus 8t squared plus 7t plus 2. Okay, dt. This whole thing here, once I plug in those values, is going to give me the square root of 14, which I pull to the outside. Why would I not do that? And then when I perform this whole calculation, the final answer is going to be 107 times the square root of 14 divided by 2. And that concludes that problem.